Okay, let's talk about alternative stable states for a minute. Um, so this idea develops that sometimes different communities develop under the same conditions in the same area under similar conditions, but they can look different. So perhaps these are alternative stable states, meaning that there can be more than one outcome. If you imagine ecology as a series of choose your own adventure games, there's a wide variety of choices you can make, and at the end, it's going to look different. Where other more purists thought, no, there's only one way things are going to work. There's competition and facilitation and disturbance, and the interaction among organisms will explain everything. Others thought, well, there's some degree of randomness, and then later we'll get into the George Sugaharas of the world that are big on stochastic events. The butterfly, beats its wings on one side of the world, something changes, that kind of stuff. So right now we're just entering the idea of alternative stable states, that stability partially depends on the scale of observation, both temporal and spatial. So Sutherland did a whole bunch of experiments of throwing or hanging tiles off the dock at the Duke Marine Station, and then would watch what happened, and based on that, presented a pretty compelling ecological story. Was later criticized by it was Wayne Susan and Connell, I believe, were the two that criticized that a bit and kind of reduced progress in the field for a little while. But let's take a look at Sutherland's experiment. So he had two dominant communities depending on what was going on. He'd have one dominated by Stiella, which is the tunicate, and the other one dominated by a bryozoan. I tried looking up how to pronounce this, and I'm terrible. So I'm going to call it, I can do it once for fun, I guess, Schizoporella? Schizoporella? Maybe. We're going to call that a bryozoan. So we have a tunicate and a bryozoan as the two main actors in this story. Both were impervious to colonization by the other species. So once one was able to dominate the tile, the other one really couldn't grab hold. And this isn't this is the same genus of tunicates. So tunicates are squishy. They filter water through a soft body. Bryozoans are clonal organisms that have a harder shell. This is a drawing of one. They're really quite pretty. Bryozoans and sponges frequently get confused for one another, but that sort of clonal filter feeding organism. So we can use the words tunicate and bryozoan from here on out. So in the next experiments, Sutherland excluded fish to see what would happen. And in the fish excluded with predation, so this is a tile without a cage on it, just his normal tile hanging off the side. Over time, the bryozoan was the dominant species with predation. Without predation, the tunicate became the dominant. So they started off with... Wait 1 second here. I thought these were associated with the dominant ones. That's the dominant ones. The color's not changing on me. Oh man. Okay, 1 second here. Okay, the year after tiles protected from the fish, predation had Stella dominated. Those exposed to domination had the bryozoan dominated. Yeah, bryozoan dominated. I guess I'm just confused here at the end because the bryozoan becomes dominated again. What happened there? Okay, give me 1 second. Oh, okay. I forgot a piece of the puzzle here. So in the without predation ones, the ones with the cages around it are tunicate is dominating, but it's an annual tunicate, so it dies in the winter, and then the bryozoan can take over. So it's showing that the types of communities, the two types of communities that developed over time, one dominated by the bryozoan and the other one dominated by the tunicate, was related to predation by the fish helping the tunicate. Predation by the fish on the tunicate is then helping the bryozoan take over. So in this one with predation, they keep the tunicates at bay, and then the bryozoan is the most dominant species. So they thought multiple states could exist and be driven by the exclusion or addition of strong interactors. And if a strong interactor is missing, the community could follow alternative stable states or trajectories. The theory developed of alternative stable states can be depicted on a topographic surface, and this is a pretty common way of doing it, where I've got a three-dimensional one I'll show here in a second. But you can imagine that the community is this ball, and this is the topography here, the series of peaks and valleys, is the potential outcome of that community, or the potential members of species within that community. So you've got one stable state here where the communities within this area can be perturbated and impacted, but it stays basically within that same well. Or you can have change where it goes from one stable state to another stable state. Then once it's in that second stable state, there's a degree of hysteresis, which is the energy it takes to move out of the stable state into another one is quite large. And so in this example, to move from here to the top where you have a tipping point and fall down requires this much energy, right? From going from here to here. But to get back to where you came from, it would take over twice as much energy. And that's a good analogy to think of when we think about declining ecosystems or changing ecosystems. If we mow down a forest and put in a soybean field, it's a lot harder to get back to where we came from than it was to change it one direction. Let's see, I've got a couple other different slides I want to show. But I'll get through these and I'll jump to my other example here. Change in one or more of the dominant species might force the ball into a new valley or stable state. The ball might not be able to move back to the first valley, and so hysteresis is the inability to shift back to the original community, even when the original conditions are restored. This is Connell and Souza complaining about the small scale and believe that alternative stable states could be driven by one species, by only species interactions, not by the physical changes in the community. And this had an impact on delaying the research of stable states for about 20 years. We're going to use some of the resilience language that's used quite a lot around this now as well. This is a pretty good one here that looking at these alternative stable states is, one example is hunting of sea otters and how that's going to affect sea urchins and kelp forests, and the interaction of the alga Culperera in the Mediterranean and Nemosis in the Black Sea. Like the additions of these species that completely change the environment are going to likely move it to a new stable state that's different than what we had before. So I want to jump over to these slides and give some examples of here. This is framed under resilience, which I think is still a good way of doing this as well. Let me see, where do we start here? So one way to think about ecosystems is in a resilience framework, and so in this framework we've got the system. It's the same diagram as before. It's just a two-dimensional. So here, hysteresis would be the energy you get from this stable state to this new stable state. But we're looking really at the resilience of the system, which is to think of, if this is our system and this is the distribution of outcomes we can have. If we take our system and bump it, we add an invasive, we add a drought, we add a small fire, we add some hunting pressure, we do some landscape modification. How hard can we knock this ball with those impacts, right? Before it no longer functions as the same system and jumps into a new system that looks fundamentally different than the first one. And that's frequently defined as resilience. How hard can we impact a system before it moves to a new ecosystem state? And that occurs once it gets over a tipping point or a threshold. I like the word tipping point, kind of Malcolm Gladwell-esque. That we can bump it really, really hard and it bounces back and forth. But once it gets that tipping point, just the slightest little breeze will knock it into a new ecosystem state and they'll look totally differently. We'll look at a couple examples of that. This is the three-dimensional figure kind of showing the same thing. This one I kind of like because you can think of it like if you've ever seen those funnels that you put a quarter in and the funnel goes around and around and around and around, you can kind of think of it like that, where instead of just going back and forth, it's the ball, which is our ecosystem state, is spinning around and around, and there's some degree of attraction at the bottom of those basins, which in that analogy would be gravity, right? If you have the funnel and you put the coin in it, it's gravity that's pulling it down. But once it reaches that tipping point, then its attraction is going to be the bottom of the adjoining ecosystem state. So it's kind of a different way of thinking about this. You can imagine if the ball is perfectly balanced right here, any small change would put it into one of these other ecosystem states, and either the first one or the second one, which could look dramatically different. So just the slightest change, rain that week, whatever it might be, would be enough for the ecosystem to fall into a different state. And so the tipping point here is quite important. This is frequently thought about in the coral reef area, in relation to coral reefs. And so coral reefs are really resilient systems that have typically a fair amount of built-in redundancy. But as that redundancy gets eroded, as we talked about in the Indian Ocean, you start to have things like sea level rise and ocean acidification and increased temperatures and loss of that redundancy via fishing and eutrophication. You start to have all this cumulative impacts. Eventually, you get to a threshold or a tipping point, and the system falls down into another stable state. And that other stable state is an algal-dominated system. So once you get to a certain point, the corals just wind up losing, and then algae comes in, and once algae gets a hold, it'll just cover the whole coral reef, and we no longer have this really interesting three-dimensional ecosystem with a lot of biodiversity. Now we have a monocrop of algae with usually a less diverse suite of players, of fish and invertebrates, etc. And so when it stays in the basin, coral reefs are quite resilient, but just about cumulative impact, just enough to get them over that threshold, and then they're declining into a totally different stable state. And it's going to take a whole lot more effort to move from the algal-dominated system back to the coral reef-dominated system. Locally, one thing I like to think about is like you cruise through the San Juan Islands, or you drive around here, and you go up to Chuckanut or whatever, and you're like, oh, this is like a beautiful natural area. Particularly in the San Juans, I think this is most prevalent, which is our landscapes are fundamentally different than they were 500 years ago, and that is the result of succession. That for thousands of years, this area was burned on a really high frequency, probably on the order of the data look like every 3 to 7 years, and that kept the forest open. That kept in kind of that mid-successional level, and that, with the forest floor open, we'd have a few large Gary oaks that would provide an open savanna-style landscape where you have an open area. This is an image of camas, really important traditional food, and you'd have acres of camas, open areas for browse. When that disturbance ended, when burning ended, then the next wave of succession came in, and we started to get in encroachment from Doug firs, which can grow up really high and shade out Gary oaks. And so over time, we'll move into this Gary oak dominated system, which would eventually get overgrown by cedars, and we move in that space. So we have two really different ecosystem states, and the reason that the Gary oak meadows that were the most dominant ecosystem here, open savanna style, like open grasslands with a few large trees, the reason that the ecosystem was maintained was via human interaction. That the human interaction of burning, of managing the landscape, would open up these areas and keep them in that stable state. Where from the loss of that burning, then we start moving over to a different stable state, which is a Gary oak dominated system. So we could think about that. This is from the clam garden world, but we could think about that in the role of what we frequently call coupled human natural systems, which is in this example, you have the natural systems and the human systems, and they're interacting in a positive feedback loop. And so in this system, we have clam gardens, and active clam management is altering the physical and biochemical properties of the environment, digging clams, turning the sediment over. All of that has benefit to the environment, and that in turn improves clam recruitment and biodiversity. Active clam management is important for indigenous health, intergenerational knowledge transfer, practicing of inherent rights, and that helps improve cultural revitalization, and that then improves the participation in clam garden management. And so both of these things are feeding back to a positive feedback loop that's maintaining this system as a clam-dominated system. So on that same three-dimensional diagram before, we could think of a Gary oak dominated system and a Doug fir dominated system, and the system might want to inherently move out of this Gary oak dominated system into a Douglas fir dominated system, but social pressure is keeping it into that Gary oak dominated system. Intervention by people via burning the landscape, which will stop small Doug firs from growing, but doesn't hurt the big Gary oaks that are growing up, that are 300, 400, 500, 600 years old, that have a large canopy shading a lot of area below them, and supporting both traditional plant foods, but also browse areas for consumed animals, things like that. Many of the traditional foods also like to be burned on a high. They're like mid-successional species. They're not early successional species, but they're kind of mid-successional species. So they need that burning disturbance and nutrient renewal. And so via human activity, we've pushed the system into a certain stable state, which is the Gary oak dominated stable state. And as that management is not practiced as frequently now, we've moved into a Doug fir dominated system. And so we've gone over that bifurcation or tipping point. In fact, we only have about 5% of Gary oaks now compared to what we had about 500 years ago. So it's been a massive decline in the Gary oak ecosystem. And it's one of those ones where most people don't really, think about it. But generally this area was pretty, had a lot of oaks, was a lot more oaks than we have now anyway. I don't want to say oak dominated because that's not entirely true, but particularly in coastal areas and the islands, you could say oak dominated. So, okay, that'll end it for the chapter 17.